Good morning. Welcome to the school. I'm, giving the first course at the school, which is the course called Introduction to Collider Physics. Let me first discuss some arrangements for these lectures. The collider physics is a phenomenological topic. It's something that has to do with the connection between theory and experiment and has a lot to do with how one understands and thinks about experimental strategies at high energy colliders. So there's a lot of data to be shown and figures that I hope you will find interesting. On the other hand, the organizers wanted me to give this talk on the blackboard, so I decided to prepare it in the following way. If you go to my website, and I think there's a link from the course webpage, www.slack.stanford.edu /Peskin, and then this page has my picture on it, and then GGI 15 in capital letters. You'll find the lecture notes for the lectures, including the figures. So if you come here and bring your computer, how many of you have your computers here now? Yeah, I really would like you to get your computer out and download the lecture notes for today's lecture, or look on with someone who has a computer. And in those lecture notes, you'll find the figures. And then I won't have to move the screen up and down. I can just refer you to what's on the web, and you'll see it much more clearly anyway. So I'm going to close this and leave it here. Take out my notes, which are the same thing you have in front of you, and we'll proceed in that way. Now, if you just start clicking on this website, you'll see that not all of the lecture notes are there, so please excuse me. But well before each lecture, the relevant lecture notes will appear on that site. And so when I want to refer to experimental data or show you some event displays, everything will be at this website. So if you folks could try and find that, I'd appreciate it. If you have any trouble, let me know in about 10 minutes whether you've not been successful. The other thing is that I'm here all week. Unfortunately, I'm leaving on Monday, but I'll be here all week, and if you want to meet me also over the weekend, we can make some arrangements. I'm in town. My office is right next door to the secretary as you go into the GGI, so if you have questions, don't restrict them to question time. And if you have questions about things that are not in the lectures, please come and ask me. It's said that when the colloquium speaker didn't show up at Caltech in the 60s, Feynman would just get up on the stage and say, "I'm Feynman, ask me anything." So I'm not Feynman, but I'll try as hard as I can if you have a question about something in particle physics. Okay, there's a little introduction which I put on the website, which gives the outline of the lectures, which is somewhat different from the one that we saw just a moment ago. So please excuse me for that. And there's also a set of references there. And so I hope you find these references useful. There are in particular two sets of lecture notes, one by me and one by Gavin Salam, which I hope you find very useful, for which the archive numbers are in that intro.pdf. Okay, last comment. There won't be any, I will assume that all of you know something about quantum field theory, roughly at the level of part one of my textbook, plus knowing something about the structure of the standard model, things like asymptotic freedom, the Higgs mechanism, et cetera, et cetera. There's not going to be any heavy quantum field theory or calculation in this talk. Rather, the emphasis is going to be on how the principles of quantum field theory connect to what we're actually seeing in events at the LHC. And so there will be a lot of, what can I say, intuition, hand-waving, showing you pictures and showing you data, but I hope it will be useful to you to give some orientation. Those of you who are going to work on LHC physics, I'm going to try and give you a lot of things that are useful to try and think about LHC physics. I'm also going to give you a lot of just straight information. The branching ratios of the Z0 and the tau lepton will appear in this lecture. And I guess it's not fashionable in this day and age to memorize things. But some of these things you really do want to memorize, because if you have them at your fingertips, you'll be able to understand very easily what's going on when you start looking at the results of experiment. So there'll be some numbers in this lecture I'm going to ask you to memorize, and I think it's might not be such a bad idea, at least one significant figure. Okay, the first lecture is going to be about collider physics at E plus E minus colliders. E plus E minus collider events are much easier to understand than events at hadron colliders, and in fact, it's going to take us 3 lectures before I want to begin to talk about the structure of events in proton-proton collisions at high energy, such as we see at the LHC. Here, what I'm going to do is to write down some relatively simple formulae that have to do with particles at high energy, and then we'll make some very straightforward applications of those to physics at electron-positron colliders, experiments that have been done in the 1990s, mainly, at the LEP collider at CERN and a collider called SLC at SLAC. In the process, we'll learn about the properties of the W and Z boson, and these are very important actors at the LHC, so we'll want to understand their properties in great detail. Okay, so first of all, I need to introduce you to one more thing, which is 2-component spinors. A lot of the intuition about particle physics has to do with spin. And I think those of you who've looked at my textbook know that I like to do this in terms of explicit spinors and amplitudes rather than the squares of cross-sections. And so in this course, we're mainly interested in particles at very high energy where we can ignore the masses. And so we're interested in thinking about fermions as 2-component spinors, either left-handed or right-handed spinning particles. And so let me just remind you of the basic formalism for that. And I'll write down some equations that we're really going to be using throughout this course. So the first step, of course, is to write down the Dirac equation. And psi is a 4-component spinor. And for the moment, just the free Dirac equation. Now we'll introduce the basis of gamma matrices that, if you've looked at my textbook, you know that this is the one that I like. It's not the best one for everything, but it's the best one for what we're going to be doing in this course, where the sigmas are 2x2 matrices. Then this equation, as you all, I hope, know, splits into 2-component equations called the Weyl equations. And those are I sigma bar dot d psi left equals 0, and I sigma dot d psi right is equal to 0. And these equations are not really independent of each other. They're related because this is the 2, 1 representation of the Lorentz group, and this guy lives in the 1, 2 representation of the Lorentz group, which is the complex conjugate of this one. So if you want to find a solution to this equation and you have a solution to that equation, you can just write this, and a solution here will give you a solution here, and vice versa. I'm also going to probably represent this as epsilon, where epsilon is the usual antisymmetric matrix. Okay. Now, we're going to be doing very specific things, so let's look at specific solutions of, to begin, the left-handed fermion equation. These are massless fermions, so this equation describes a left-handed spinning fermion moving at the speed of light, and its right-handed spinning antiparticle. The solution is, for the free particle, looks like this. If I write out this equation, P is P, let's look at the particle moving in the 3 direction. So that's the 4 vector. The equation is then P plus P dot sigma, or with this vector P sigma 3, when U is equal to 0. Or in other words, U is something that's only in the sigma 3 equals minus 1 component. U is equal to 1, 0, and we normalize these U's to U dagger U is equal to 2p0. So we need a square root of 2p here. The other kind of solution to this equation, relativistic equations always have both positive and negative energy solutions, is the negative energy solution. And that's the solution that represents the antiparticle. We'll call that VR because it's a right-handed spinning antiparticle, e to the plus I p dot x. The equation is actually the same. So the spinner is the same. What you get then is a left-handed spinner, but remember, this is the wave function of the particle that when you take it out gives you a hole, which is the antiparticle. So the spin is the opposite of the physical spin. And then, in the same way, we can solve for the spinners of the right-handed particles. There's one more thing I wanted to do. When we use these particles, they're not always traveling in the 3 direction. And so we've got to then rotate them into the orientation in which we want to use them. So if I take these spinners and, oh, sorry, that should be a +1. If I take these spinners and I rotate them, typically the kinematics that we're going to use to define a reaction is the following. The 3 direction going like this. I'm going to try, just to avoid lots of I's that are hard to keep track of, having the reaction plane being the 3-1 plane. So we need to rotate things into the, by theta, and then we'll get UL of P is the square root of 2p minus sine theta over 2 because it's a spin-a-half particle, and the same spinner for the right-handed particle. And then if I were to solve the equation, I would naturally get something that starts with 1, 0, and then I rotate it. So UR of P cosine theta over 2 sine theta over 2 is the same as VL of P. So maybe I ought to just record these things for your memory over here. And let me write it in the following way. UL equals VR equals the thing that I wrote there. And if I want the particle that's colliding with it, the one coming from the opposite direction, I have to rotate through an additional 180 degrees. So that gives this spinner. And similarly, UR and VL are given by this one. And the particle which is 180 degrees away from that is the same as this one. So if we just keep those on a piece of paper somewhere, we can very easily do computations that involve external states, which are these 2 component spinners. And if we're at high energy, we don't care about the masses. That's a very small correction. So we'll get most of the physics of what happens when you put these states together. So more or less at arbitrary times during the week, I'm going to pull these spinners out and do some computations with them, and I just hope you're very comfortable with that. Okay. Let's see. I'm going to go rolling along, but if you have questions, raise your hand, and if I don't notice you, start shouting and being anxious. Any questions at this stage, though? Oh. Excuse me. It's right over here. Is it right in the notes? That's the most important thing. Sorry? Okay. Good. Now, we're also going to be dealing with vector bosons. And for vector bosons, they also have spin and they also have polarization vectors. And so the next task is to get those up on the blackboard so that we can deal with those in a very straightforward way. So for a vector particle, the polarization vectors are much easier to understand. They're just basically ordinary vectors. A massive vector boson in its rest frame can have a polarization vector that points in any one of the three directions, 1, 2, and 3. And it's useful to organize those, as I've done with the spinners, into polarization vectors that correspond to definite angular momentum. So for a right-handed W boson, let's say, that's the polarization vector at rest. For something that has J0 equals 3, the so-called longitudinal polarization vector, I'll write the polarization vector that way. And for a left-handed W boson at rest, that's the polarization vector. So once again, these are the three vectors that we would like to understand. And now, of course, this is just what happens at rest. Now we have to talk about what happens when we put the W boson in motion. So let me now perform a boost along the three axes. So the first one remains the same. The last one remains the same because the components are all transverse to the boost. The middle one, something odd happens. It becomes this vector P over M, 0, 0, E over M. So this is the gamma factor of the boost. This is decidedly weird because this thing is supposed to be a polarization vector, but it looks like its components are growing without bound. And actually, this has the odd feature that it becomes parallel to the momentum vector at very high energy. At the same time, you can see that the Lorentz product of this with the momentum vector is 0. That was true here, so it ought to be true in any boosted frame. So there's something here that we really need to understand, because it seems very odd that you can get some large numbers appearing in your quantum amplitudes if you have very energetic W bosons. And later in this course, there's going to be a whole lecture on that topic. It's the 5th lecture of the series. For the moment, I'm going to ignore this. And in fact, mainly I'm going to work just with these two transverse polarization vectors. So the issue I've just raised, it's coming in lecture 5, but I think until then we can just put it aside. Once again, it'll be useful to think about what happens when you rotate these vectors. And so R and L, 1 over the square root of 2, 0, cosine theta plus or minus 1 minus sine theta is the rotated version. And if P is the momentum, let me make this definition, and that vector will come up from time to time as we discuss the properties of W and Z bosons and photons that we have at colliders. Okay, so that, I guess, completes the kind of formalism that I wanted to describe. Now we come to applications. But we'll start simple. I think the very simplest application of all of these formulae is just to compute the well-known quantum electrodynamics process, E plus E minus to mu plus mu minus. And so let's just warm up by computing the cross-section for this process. Before I do that, any questions? Still happy? Okay, if you're not happy, let me know. Okay. So this is pretty easy, and probably if you've studied quantum field theory, you've seen this before. An electron comes in, a positron, a muon goes out with an anti-muon, K, P, P bar, and K bar. These guys in the amplitude are described by the spinors, which are on that blackboard. I'm going to consider for definiteness a left-handed electron and a right-handed positron. And the matrix element for this process, for the moment just in quantum electrodynamics, is something like this. Minus I over Q squared times V bar of P bar sigma mu U of P. So already I'm specializing here to two-component fermions. And for the final state, something like this. Okay. Good. The basic ingredients are these products of two-component spinors. And so now comes the first point in the lecture, and not the last, where I'm just going to pull those out of this blackboard over here and start computing with them. So let's just compute this element using this and this coming from the other direction. Actually, why don't we just line them up with the 3-axis? That'll be a whole lot easier. So the square root of 2p minus 1, 0, or sorry, 1 minus sigma mu 0, 1. Okay, this guy's up and this guy's down. So only sigma 1 and sigma 2 are going to contribute here. So we get 2p minus sign 0, 1. I always get this wrong. I minus I 0. And that's pretty simple. That's just actually one of the vectors that we already met over here times epsilon L of P, where that's the vector boson polarization vector for left-handed spinning polarization. And this is all pretty easy to understand. If I have a left-handed electron and a right-handed positron that are coming in along the 3-axis, this guy has half a unit of spin in that direction. This guy has half a unit of spin in the same direction. And so when we end up with a virtual photon, it has 1 unit of spin in the left-handed sense. And so this calculation can be then a basic building block that we can use. I guess I might as well just show you that it's no accident. If we were to do this in a general orientation, we would have, I guess, cosine theta over 2 sine theta over 2. One sigma sine theta over 2 cosine theta over 2. For the one component, we get that times that plus that times that, which is 0. For sigma 1, we're going to get, there's an overall minus sign, cosine squared theta over 2 minus sine squared theta over 2. For the I, we'll get minus I cosine squared theta over 2 plus sine squared theta over 2. And for the 3 component, it's cosine sine both answers give the same result, and there's a minus sign in it. So this adds up to the result that I wrote before for the vector boson polarization vector. So this equation that I wrote here is actually true for any orientation, as it should be. When I compute this vector matrix element of 2-component spinors, what I get is the left-handed polarization vector along the direction of the incoming electron. As you can imagine, if I did this with right-handed spinors, you can check yourself, you get exactly the same thing. I forget whether there's a minus sign here, please excuse me. The right-handed polarization vector. Okay. Well, now, I hope this is all very simple, but we're already at the point where we can get some physics out of this. Because if I compute this matrix element, this is just I e squared over q squared. Each of these is going to contribute a 2p, which is just q, so there's a q squared. And then what's left, there's an extra factor of 2, I guess, is a dot product of 2 of these vector polarization vectors. Epsilon L of p dot, in this case, epsilon L star of k. So if you just take that matrix element, dot this vector into 1, I, 0, what you're going to get here is 1 plus cosine theta. And similarly, if the helicities didn't match, if you had L times R, you get 1 minus cosine theta. So now, in a very simple way, I'll just let you guys clean up all the factors. We basically have a physical prediction for the form of this matrix element. d sigma d cosine theta for e plus e minus goes to mu plus mu minus for all left. Or actually, if we did it the other way around, with an e minus right and a mu minus right, we get pi alpha squared over 2s times 1 plus cosine theta squared. For left going to right, or for right going to left, we get the same answer, but with 1 minus cosine theta squared. And then from that, you can basically put together all the features of the electron-positron, the 2 fermions annihilation cross-section. So, oh, and then all the other possibilities are 0 by helicity conservation. So then, for example, you get the very famous and well-known results that if you were to consider just E plus E minus to mu plus mu minus unpolarized, that has an angular distribution which is the average of these two, which is 1 plus cosine squared theta, some distribution that as a function of cosine theta looks something like that. And also you can get the well-known result for the total cross-section, 4/3 pi alpha squared over s. So as you see, these are very basic features of the simplest quantum electrodynamics cross-section. And what I wanted to persuade you of is that they're very easily obtained when you go to the massless, you go to the high energy limit, you ignore all the masses, you use the two-component spinors in the simple way, just do a little computation, and there you are. Okay. Well, now we're doing extremely well, and now we can go on to the physics of the W and Z bosons. So more or less everything that I've just explained to you, there's hardly any more physics that comes in when you talk about the W and Z bosons. The only things that you have to do are be careful about the actual structure of the couplings in the standard model, getting all the numerical factors in the right place. And so let me just start with that. So first of all, I ought to emphasize that this spinology that we've just been doing also applies to vector boson, not only to two fermion couplings to two fermions, but in this process we had an intermediate vector in the intermediate state to vector boson couplings to two fermions. So for example, you folks always know that a W boson, let me say W minus, decays to a left-handed lepton and a right-handed antineutrino. So the matrix element for this process will be some factor, which we'll discuss in just a moment, times the W polarization vector, dotted into the same object that we've been talking about. U dagger of P, sigma bar mu, V of P bar for the lepton and the neutrino. What that means is that we can immediately evaluate this. 2p times the square root of 2 times the left-handed polarization vector star of p. Now, if I take the W polarizations, let's say along the 3 direction, so my W is polarized in some way in the 3 direction. The leptons go off at an angle theta, so I have to rotate by theta. It's more or less the same computation that I did here. And so we can immediately write down the answer. The matrix elements for right-handed 0 and left-handed polarization, the W at rest, will be proportional to 1 plus cosine theta, 1 minus cosine theta, and the square root of 2 sine theta. And then if I square these, I'll get the angular distributions. So for this setup, a W minus, a negative lepton, the decay angle defined in the way that I've described, what we have is the following distribution as a function of cosine theta from 1 to minus 1. A left-handed W boson has a decay distribution which is 1 plus cosine theta. a right-handed W minus boson has a decay distribution which is 1 plus cosine theta, 1 minus cosine theta squared, and a longitudinally polarized distribution, longitudinally polarized W boson has a distribution which is 2 sine squared theta, and it just lines up something like that. So now, actually, we already know something about the properties of W bosons at colliders. If you have a W boson at a collider, and you manage to get into its rest frame, and then you look at it in terms of its decay to a lepton, the forward leptons correspond to a left-handed polarized W minus, or maybe I should say a right-handed polarized W plus. The backward leptons correspond to a right-handed polarized W minus, or a left-handed polarized W plus. And the leptons that are in the central region of that decay angle cosine theta correspond to the longitudinally polarized ones. So already we're getting to a point where we have some kind of analysis tool. If you have a W boson, if you completely reconstruct the event, you measure this angle, you can determine the W polarization, and that's going to, excuse me, tell you something about the dynamics of the reaction. And so this is the kind of information that we're going to try to use when we go to the much more complicated setting of the LHC events and try and understand in detail what's happening in a given class of events that we want to analyze. This picture is probably one that you want to memorize. So, very good. Okay. Now, it'll just be good to have the coupling schemes of the W and Z, because they're going to be, again, important objects in this study. And so let's go through and talk about that. The couplings of the W and Z come from the covariant derivatives of the standard model. And so anyone in this room who has not written down the Lagrangian of the standard model? Okay, if you don't want to admit it, you can come by my office and admit it in secret. But I hope you've all seen this before. The coupling to the photon, F bar gamma mu F, and E, and then the electric charge appears here. The coupling to the W has a G over the square root of 2 in it for W plus, let's say, and U bar gamma mu left-handed projector, or maybe left-handed particle, D. The coupling to the Z is the one that it's always kind of a struggle to remember. It's G over CW, or maybe E over SW CW. For each chiral species, F bar gamma mu, and then something called QZ F, where QZ is the weak isospin minus SW squared times the hypercharge. And in this set of lectures, I'm always going to have CW as cosine theta W and SW as sine theta W. So once again, I hope this is something that you folks have seen in a previous course in quantum field theory or particle physics. If you need an explanation of this, come see me this afternoon and we'll work through it. Now, having written down that Lagrangian, it's now, I'm sorry? Good. Having written down that Lagrangian, it's very easy with the tools that we have to work out the detailed properties of the W and the Z. So let's just start with the W. And let's start with the simplest decay. W minus goes to, let's say, an electron and an electron antineutrino. First of all, only left-handed electrons and right-handed antineutrinos appear, according to this. The matrix element is Ig over the square root of 2. There's a W polarization vector. There's the same collection of spinors that we've just been talking about. So now this is something that's very easy to evaluate. Ig over the square root of 2, 2p, which is the same thing as the W mass, the square root of 2, and the product of the two polarization vectors. The square of this, let's not worry about angle. I just told you everything you need to know about the angular dependence of the decay, is g squared mw squared. And this is the product of two vectors, but if we average, for example, over the W polarization or integrate over the angle of the lepton, we're going to get a third as the average of the square of that. And that's pretty much it. Gamma is equal to 1 over 2 mw, phase space, the value of the matrix element, and I'm going to write the answer in the following way. Alpha weak times mw divided by 12. That's very simple. The only problems here are notation. And once again, I need to introduce some notation to try and make this as straightforward as possible. So let me now pause to talk about the coupling constants in standard model phenomenology. Now, you folks all know that coupling constants run under the renormalization group. So you have to choose a definite reference point and quote couplings in relation to that point. And then if you want a different point, you use the renormalization group to go between one and the other. But a very convenient point is to take as the reference point Q equals the mass of the Z boson, because at that point there are some precision experiments that tell you exactly what the various coupling constants are. And so let's just make a list of standard model coupling constants that go along with the standard model Lagrangian with the couplings evaluated at this point. So first of all, alpha, that's e squared over 4 pi, and the value there is 1 over 128, not 1 over 137. Secondly, I'm going to define alpha weak as g squared over 4 pi. As you know, g is e divided by SW in the standard model. And this is something like 1 over 29.6. Alpha weak prime, g prime squared over 4 pi, is about 1 over 98. And this all goes along with a measured value for the weak mixing angle, sine squared theta w, which is something like 0.231. And, well, maybe I might as well just add to this alpha s the value of the strong interaction coupling at the same reference point. It's 1 over, I think, 8.5. So this is a very important property of the standard model. There isn't much range among these coupling constants. The strong interaction coupling constant at high energy, you all know, because of asymptotic freedom, is a weak coupling. It's not more than a factor of 3 or 4 larger, though, than the weak interaction coupling. The weak interactions, of course, aren't weak because they have a small coupling. They're weak because in radioactive decay, the W mass is large. So all of these interactions can be treated by perturbation theory. And except for some funny things that we're going to talk about with the strong interaction in lecture 3, they're pretty much all on the same footing. And so in order to do precision calculation, we're going to have to go to comparable orders in all of these couplings to get high precision theoretical results that we can compare to experiment. By the way, these values are probably also worth memorizing. and being able to pull out of your hat when you want to make a numerical estimate. Okay. Well, now we're pretty much all set to understand everything that we want to know about the W boson. We've already described the angular distribution of its decays. The only remaining thing we need are the total width and the branching ratios. The partial width is given by this expression, and so the total width would just be that expression times 3, because there are 3 leptons, and 2, because there are 2 quark doublets that we can decay to. To the accuracy where I'm working, I can ignore CKM mixing. But if you put it in, it really doesn't make much difference. And then you have to remember that there's a non-trivial QCD correction, which to first order is just alpha S over pi. So, and I'm sorry, I forgot color. So this number is actually not 3, it's something like 3.1. And if you add up all those things, you get 2.1 GeV, which is a number that is resolvable in LHC experiments, but it's not really important. Essentially, the experimental resolution on the width of a peak in W bosons is larger than this. The branching ratios are also apparent from this expression. For E, mu, and tau are equal, and they're about 11%. The branching ratio for the various quarks is a little larger because of this factor, 34% each. And so armed with this information, you can really understand quite a bit. If there's a W cross-section, what fraction comes out as electrons or taus, what fraction comes out as quarks. These are things that are going to come up in the course of the lectures. So it's good to have these numbers and be able to estimate those things. Okay. Now, one of the consequences of this analysis is that the W actually does decay to a large number of different things. And I just thought I'd illustrate that by presenting some event displays from the experiments at LEP, the Large Electron-Positron Collider that operated at CERN in the 1990s in what is now called the LHC tunnel. So there's a picture in the notes of what it looks like for an electron-positron to annihilate into a WW that then turns into either 2 leptons, having leptonic decays on both sides, or a lepton and a quark, having a leptonic decay on one side and a quark decay on the other, or when you have QQ bar, so both quark decays, you end up with some more complex mess of particles whose nature we're going to discuss in greater detail in the course of these lectures. Okay. Any questions about the W before we go on to the Z? This isn't hard. It's just kind of essential background. And so let's just march on then. Okay. For the Z, there's not much more that we have to learn than what's on this blackboard. The essential differences are that the Z can now decay to either left-handed or right-handed particles. However, the angular distributions, I've already explained to you the spinology of that. Right now, we only want to get the normalization of the various Z decays. The main features are that for the Z, square root of 2 is not there. Instead, there's a factor of QZ, the formula that you might remember had written on this blackboard. Oh, sorry, and a cosine theta W. So pretty much we can just immediately write down the answer for the Z partial widths, Z to FF bar, where F is a chiral species of fermion, is alpha weak over 6 CW squared times MZ times QF squared, whatever that is. And so the whole pattern of the decay depends on the values of the QFs. And the QZFs. And let me just remind you that this is I3 minus SW squared times Q. So the next order of business is to make a table of the QFs and work out all the branching ratios of the Z boson. So that's pretty easy, so let's do that. Now, when we tabulate the QFs, there are two combinations of the QFs that are particularly important. So let me introduce those first. One is that if I can decay both to left-handed and to right-handed particles, the total rate is going to be the sum of the squares of the amplitudes. And so it's useful to define the SF, which is the QF for the left-handed particle, plus the QZF for the right-handed particle. The second is that these two Qs are different because the I3 is chiral. It's plus or minus half for a left-handed particle, but 0 for a right-handed particle. And what that's generally going to mean is that the Z decay is asymmetric between left-handed fermions and right-handed fermions. So let me also define A sub F is QL squared minus QR squared over QL squared plus QR squared. So this is the polarization asymmetry, which typically favors the left-handed species over the right-handed species, as we'll see. Okay, well now it's easy. We write down neutrinos, electrons, up quarks and down quarks. We write down the QL. We write down the QR. We write down the SF, and we write down the AF. And to evaluate SF and AF, I'm going to use the numbers for sine squared theta W 0.23, unfortunately on the blackboard that I just erased. So let me try and get this right. The theoretical values are pretty easy. I'm just copying off of that formula. Okay, now you take out your calculator and you punch it in, and the following comes out. 0.25 and 1, 0.126, and 15%, 0.144, and 67%, because these terms are getting small now. And 0.185, I think, and 93%. Okay. It's interesting, actually. I mean, these are all just ordinary quarks and leptons, and the formulae are all the same, but the numbers are different. And it's now interesting to go experiment, are these really the right numbers? And so let's be a little more concrete about that, and then we'll talk about how it works. Okay. So first of all, the total width. So that is alpha W mz divided by 6CW squared. Yeah, I even wrote that correctly. Okay. 3 neutrinos. I'm just picking now numbers from this column. 3 leptons. 2 up quarks because the top quark isn't heavy enough to be produced in Z decays. So 2 times this number 3.1 again, times 0.144. And there are 3 species of down quarks, but there's a kind of exception for the bottom quark. So the right number instead of 3 is 2.96. I'll explain that in a moment. Times 3.1 times 185. And now if you put all those numbers together, you get 2.49 GeV. A little larger, significantly larger, but not than the W width, but not huge. The branching ratios that follow from this formula, let me just write them down as well. For a neutrino species, it's 6.7%. For a lepton species, it's 2.3%. For an up quark species, it's 11.9%. And for a down quark species, it's 15.3%, and just slightly smaller for the bottom quark. The problem with the bottom quark is that there are some diagrams that, even at this modest level of accuracy, one shouldn't omit. Namely, the Z can turn into 2 virtual W bosons, which then give a top quark. Or the Z can just couple directly to virtual top quarks, which then turn into bottom quarks. So these diagrams produce a few percent lowering of the B rate, and it's actually significant, as we'll see in a moment. These numbers, if you're only worried about LHC physics, have very important implications. As we'll discuss in Lecture 4, it's very difficult to do anything with Z decays to hadrons. People do things, but it's much more difficult. The easy Z decay to C is the Z decay to leptons. But if you omit the tau lepton and you just look at electrons and muons, that's only 4.6% of the total Z production rate. So you're always starved for statistics, if you like, if you look for Z's in their leptonic mode, whereas that's the very straightforward thing to do at the LHC. It's an important point which is already apparent in these numbers. Similarly, if I multiply this by 3 neutrinos, this turns into a 20% branching ratio, which means that 20% of the Z's that you make at the LHC are just totally invisible, like no chance to see them in a detector. And they produce unbalanced momentum, which is going to be a signature of new particles. So this is a very important source of backgrounds. Similarly here, the B's are only roughly this branching ratio. And so if you're interested in Z to B, the branching ratio is substantial but not overwhelming. And this is something also that becomes very important in collider physics. So these numbers are interesting in their own right. They're checkable in experiment. And they also have important implications when you try and do physics at the LHC using the Z as a tool. Then in the next few slides, if you look in the notes, you'll see some event displays. So the LEP experiments, for some reason, weren't very nice about this. But my colleagues in the SLD experiment at SLAC were very nice to post a lot of very beautiful event displays, and I have a little collection of them here for you. So you can see what an event display looks like for E plus E minus, for tau plus tau minus, and for a Z decay to QQ bar. And for the Z decay to QQ bar, you see the same thing that we saw in the W decay to quarks. What seems to be QQ bar is manifested as not two tracks that go back to back, but as a stream of tracks, a whole bunch of pions and kaons, which are all moving in the same direction, or if you have QQ bar moving back to back. Now, you probably know that this is what has to happen because quarks are confined. You don't see in nature physical fractionally charged particles. Instead, you always see quarks in bound states. But nevertheless, how the structure forms is going to be very important in LHC physics. And this is one of the main topics that I'm going to deal with in Lecture 3. But for the moment, I'd just like you to remember that whenever you produce a quark or a gluon, what you see is a stream of hadrons, fairly collimated, very visible on an event display, and those things are called jets. And there'll be a lot about the physics of jets in Lectures 3 and 4 of this series. Let me tell you one thing about the z decay to jets, which is very interesting. The jet is made up mainly of pions. Pions are spin-zero particles. And so you might wonder a little about the spinology of the distribution of jets. What is the angular distribution of jets as opposed to quarks? What we predicted for quarks is that the distribution would be 1 plus cosine squared theta. Let's see, it's some combination of 1 plus cosine theta and 1 minus cosine theta. But if we don't distinguish between particles and antiparticles, which is quite hard for quarks, we average the two. It's 1 plus cosine squared theta. What about the distribution of jets? Well, for each jet, you can see from the picture there's going to be some definite axis. And I'll show you how to quantify that in a later lecture. And you can look at the distribution of the jet axes with respect to the z orientation, which is given by the beam orientation. So I actually put the data for that. It's a little later on. If you page through a couple pages, after page 15, you'll see that. This is the distribution measured by the Aleph detector at LEP at the z0. And you see it's a beautiful 1 plus cosine squared theta distribution. So the jets follow the direction that was predicted for the quarks. And why that's true and how the jets are made up, again, we're going to discuss in more detail in a later lecture. Okay, now I've shown you these pictures, but I really ought to say something about how these pictures are made. And so please turn back a little to the figure which shows the schematic of the opal detector, which was used at LEP. So, in this lecture course, it's only theoretical physics. There are no experimenters. So I have to take, I guess, a few minutes of your time and pretend to be an experimenter, which I'm not, and tell you a little about this technology. By the way, how many of you have spent a summer at CERN? Raise your hands high. Okay, so you've had some experience hanging around collider detectors and analyzing data. And that's a good experience. Those of you who haven't had that experience should try and get it. Because it's very good to have, as we've talked about with these numbers about the branching ratios and the coupling constants, some kind of tactile knowledge of how these experiments take data. But assuming that the rest of you are just ordinary theory students who've just had your nose in books for a long time, I have to give you a 5-minute introduction to what experimental detectors look like in particle physics. Okay, so the idea of a particle physics detector, the kind that we're interested in for high momentum transfer LHC physics, is that we want to bring together two beams of particles, have them collide at a definite point, which will be then inside the detector. Particles then come out, and what we have to do is to put in devices that are going to image as many aspects of that interaction as possible. Essentially, each interaction, we only get one shot at it, so we have to measure as many components of that interaction simultaneously as we can. So I listed in the notes a variety of components that you might want to think about, namely electrons, photons, here we go, electrons, photons, muons, charged, strongly interacting particles, for example, pions and protons, neutral strongly interacting particles. For example, K zeros or lambda zeros. Maybe I should just say that most of the photons at the LHC are coming from pi 0 decay, which more or less immediately, on the scale of anything else that happens, the pi 0 decays to 2 photons. And then finally, at the bottom of this list, neutrinos. And we've got to do all that at once. It doesn't help to measure the charged particles in one event and the neutral particles in the other event, because by quantum mechanics, every event is different. So how do you do that? Well, there's a general plan for this that emerged for the first time in the what was called the Mark I detector at SLAC in the 1970s. This is a very famous experiment because it measured the psi particle, it discovered the tau lepton, it discovered the jetty nature of E plus E minus, but it also introduced the canonical plan that's been used for collider detectors ever since. So the idea is to think about the collider detectors from the inside out. So we have the collision point, and then we want to put around that various kinds of experimental devices. And the basic idea is that the particles have to go through all the layers, and so you have to put those things in the center that will interfere minimally with the things in outer layers, although everything you put in interferes to some extent, and that's just something you have to live with. So typically you have in the center some kind of volume which is an ionization detector, which then can detect the path of tracks. And we'll have a solenoidal, so this is a barrel, as you see in the diagram of the opal detector, a solenoidal magnetic field that bends tracks, and either a gas chamber or some layers of silicon to get space points along that track. The curvature of the track then tells you, and knowing the magnetic field, tells you the momentum. And so to some extent we've taken care of charged particles of these kinds. Then the next thing you want to do is to measure the electromagnetic component. And so you have a device there called an electromagnetic calorimeter. Now, an important property of particle interactions at high energy is that electrons and photons with energies well above the electron mass, let's say above 10 or 20 MeV, initiate electromagnetic showers. In a material, an electron or a photon will come in, the electron will interact with the material and radiate a hard photon. A photon will come in and do a pair conversion to an E plus E minus pair. Then, another depth of material in, these guys will emit photons, then another depth of material in, these guys will make pairs, etc. Eventually one has a cascade with a very large number of ionizing particles, all electrons and positrons. If I now measure the ionization, I get a measure of the total energy of what came in. The characteristic distance here is called the radiation length. In a high Z material like lead, this distance is about half a centimeter. So if I pile up 15 centimeters of lead, of course with detectors in the middle, then I can make a good measurement of the energy of an electron or photon that comes through that. And so I want some high density material that goes in here. In the LHC environment, in Atlas, they have, in fact, lead swimming in a pool of liquid argon that you use to gather the ionization. CMS has a somewhat more sophisticated system where they have crystals of stuff called bismuth tungstate. So those are two metals from the bottom row of the periodic table that form a glass that looks like glass, but it feels like a lead brick. And it produces the same effect, and you get scintillation light, which measures the energy that came in. Then outside of that, you think about the particles. So we've now taken care of these. And in particular, we've discriminated electrons from photons. Now, 15 centimeters of lead is a little less than 1 nuclear interaction length. So if we put a lot more stuff, we can get the same kind of shower where a pi plus comes in. It turns into more pi pluses, which then hit nuclei downstream, and again shower. And so that component that's out here, typically you would make that out of some lower Z material. It's cheaper and you don't need to, it's hard to get the precision of an electromagnetic calorimeter. And then if this is deep enough, anything that gets through the whole thing is a muon. And in the LHC detectors, one even puts more ionization counters out here to image these muons on the outside of the detector. So in 5 minutes or so, that's how you do elementary particle physics. I hope there are no experimenters in the audience. Just for your guidance, and again, these are very rough things, but again, some numbers that you might want to have in your head. It's important to understand, oh, and then the neutrinos, it's hopeless. Okay, you need, tens of kilometers of material. So this part is hopeless, but we've taken care of everything else in one way or another. There are interesting ideas about how you put these components together. For example, in CMS, they use both the tracking and the calorimetry to try and understand the hadron calorimetry. Some kind of guidance about how well you do. And I think this is really more relevant for the dependence on energy. Delta P over P from tracking is the most precise. I think a kind of canonical number would be something like 3% for 100 GeV particle. But then that's the dependence, so it degrades as the momentum gets large. Essentially, the track is stiff and you can't measure its curvature. Electromagnetic calorimetry works the other way. Delta E over E, 10% is a reasonable number, and then it's 1 over the square root of the energy in GeV. And for hadron calorimetry, something more like 50 to 70%, and again, 1 over the square root of E in GeV. So electromagnetic calorimetry is always better than hadron calorimetry. Both of these get better at high energy. This gets worse at high energy, and that's a problem. So some combination of these is necessary in order to try and understand the structure of an event. And of course, if you propose a signature like 3 TeV muons are going to come out of your favorite new particle, you should understand whether, where the boundary is when you can't tell whether those muons have positive or negative sign, something else that follows from this equation. Okay. There are some other special cases that I'd just like to point out. One problem with this design is that to do the tracking, you need a solenoidal magnetic field. But that means there has to be a magnet somewhere. But a magnet, in modern technology, a superconducting magnet that lives in a cryostat, has a couple radiation lengths of material in it. So if you put the magnet on the inside, you spoil the electromagnetic calorimetry. On the other hand, if you put the magnet on the outside, you can't afford it. And so there's a compromise that you have to make. Atlas actually has the magnet on the inside with some kind of counters on the inside to look at the initiation of showers. And they have to model very carefully what comes out of all this material. CMS actually puts the electromagnetic and some of the hadron calorimetry inside the magnet. But it means their hadron calorimeter is very thin, so it can't really achieve this level of resolution. So one way or another, there's always a compromise when you have to actually design a detector. And this is what experimenters spend a lot of time worrying about. Well, there are also things like you want all these electronics channels to be implemented, and then you need cables to get the signals out, but the cables are not detectors, so then things can just get lost there. It's very complicated. Okay. There's some also special considerations for the third generation particles. The bottom quark is a very interesting object. It has a lifetime of 1.5 picoseconds, which corresponds to a c-tau, which is something like half a millimeter. But half a millimeter is actually something you can image in a modern tracking detector if you put some silicon layers within a couple centimeters of the interaction point. And so both in Atlas and CMS, there's a dedicated vertex tracker that images the tracks, gets ionization space points from the tracks that just come out of the interaction region. And so typically you'll have something like particles coming out and then tracks that come not to the vertex but to some point which is displaced from it by, with a Lorentz boost, a few millimeters. And so this kind of thing is called a vertex tag for a B quark. There's a whole science associated with it that I don't have time to discuss here. And so you can talk about identifying bottom quarks in events. To a certain extent, you can do this with charm quarks, which have a somewhat lower lifetime. The other kind of special particle that you should think about is the tau lepton. Like the W boson, the tau lepton has a variety of decays, both leptonic and hadronic. And I think I won't write these on the blackboard, but I put in the notes the main branching channels of tau lepton decays. When you reconstruct tau leptons at colliders, you have to think about, is the tau decaying to an electron, a muon, a pion, some heavier hadron? How many tracks is it making? Each choice there is, in general, a different physics analysis. And all of those have to be combined if you want to think about taus in the final state. Typically, there's one which is the best, but the best one can be different for different kinds of analyses that you might want to do. Maybe in the 7th lecture, there'll be some examples of that. Okay. Finally, for this discussion of experimentation at the Z boson, I'd like to just write some numbers which are measurements corresponding to the numbers that I wrote, these estimates that I wrote on the blackboard, just to show you that this is not just theory, but actually the connection between theory and experiment is really very strong. So let me write a couple of these quantities. So first of all, we can, from the Z branching ratios, we can define RL, which is the ratio of Z to hadrons divided by Z to some lepton, like mu plus mu minus. So in these tables that I'm going to make now, I'm going to write the number from the analysis that I just gave you, the standard model number including order alpha corrections based on the best fit to the value of sine squared theta W, and then the experimental number. And the error in the last decimal place in these columns will be in parentheses. So here, if you just take the numbers I gave you, the ratio is 20.6. If you do a proper standard model analysis, including higher order corrections, you get the error in these decimal places. And the experimental value is 20.767 with an error of 25. So this is a very well understood number. Here are two more. RB, Z to BB bar, divided by Z to all hadrons. From the estimate that I gave you earlier, 0.213, full standard model corrections, 0.21562, with an error of 13 in the last places. And from experiment, 0.29, with an error of 66 in the last decimal places. And finally, for the total width of the Z, I gave you 2.49 before. The measurement is 2.496, the theory is 2.4965, and the measurement is 2.4952. So you can really see that the standard model works extremely well for predicting the properties of the Z boson. These are just examples of a very large number of measurements that were done in the physics program of the LEP and SLC. One more example that I'd like to give you here is the case of the asymmetries. Remember, I told you when I made that table on this blackboard that the various standard model species have different polarization asymmetries. That is a preponderance of left-handed over right-handed particles in the ZDK. It's possible to measure these in various ways. One way is to use the weak interactions of the tau lepton to measure the tau polarization. Another way that actually was done at SLAC is to produce a polarized electron beam and use the angular distribution or even the cross-section. I mean, if you have left-handed electrons making Z's and you have right-handed electrons making Z's, you can measure the ratio of those two couplings and get at these asymmetries. So here are three of those numbers. For electrons, we predicted the asymmetry of 0.15. If you're much more careful, 0.1480 with an error of 11 here. And the experimental number is 0.513. Okay. For taus, the same predictions. And 0.1463. And for bottom quarks, so you use polarized beams, you find bottom quarks, you look at the angular distribution, you find bottom quarks with this vertex tagging technique that I told you before. We had written 0.93. The standard model corrected number is 0.9346, very accurately actually. And the experimental number is 923 with an error of 20. So once again, it's amazing that these numbers are really different, even though the underlying physics of these couplings is the same. And it's even more amazing that nature actually agrees with that in a very striking way. So I think probably we're coming to the end of the hour. Let me just say there's one more thing in the lecture notes that I put in there, which you might want to just study on your own. It's a computation, and it kind of covers the blackboard, so I think I'm going to stop before I do this. These asymmetries are reflected not only in the properties of the Z decays, these specific things that I've talked about here, but also in the forward-backward asymmetries for unpolarized E plus E minus to FF bar processes, both at the Z and above the Z. And so if we write the cross-section for E plus E minus to FF bar, that's an average of 4 different cross-sections. One in which the electron left goes to the F left, one in which the electron left goes to the F right, electron right to F right, one in which the electron left goes to the F right, and one in which the electron right goes to the F left. Now, these guys here have the angular dependence 1 plus cosine theta squared. These guys here have the cosine theta squared. So if the amplitudes are all the same as they are in QED, you just get the average of these. But in the weak interaction theory, it's more complicated. There's interference between the photon diagram and the Z diagram. And it's constructive interference for these cases. And it's destructive interference for these cases. So the larger effect has this angular distribution, leading to an order 1 forward-backward asymmetry in those processes. And you can trace this and measure it in experiment. There's an interesting property which is shown in the notes that at high energy, I say energy much larger than mz, but you can see it already at the highest LEP energies of 200 GeV. This basically goes over to what you would expect for an unbroken SU2 cross U1 theory, where you exchange the A and the B bosons. So even at the highest LEP energies, we're seeing the situation where SU2 cross U1, spontaneous symmetry breaking is restored, and that idea gives the main properties of E plus E minus to 2 fermion processes at those energies. The idea of comparing this kind of calculation to unbroken SU2 cross U1 is something that comes up a lot when you think about physics at high energies, and we'll make reference to it at various points when we talk about LHC physics as well. So that's a good place to stop for today, and tomorrow I'll take up how we generalize all this to reactions with hadronic initial states. So thank you very much. Okay, I guess any questions at this point? This would be a good time to ask them. Please.
About the decay width of the Z boson, the fact that the experimental value is lower than the theoretical one, what should we think about that?
Sorry, what?
The experimental value is lower for
what?
the decay width of the Z boson. The total decay width. Yeah, now it's erased. It was.
Oh, I'm sorry. It is erased, unfortunately.
It's on page, the 24th page of the note.
I'm sorry, but the experimental value is lower in the 4th decimal place.
Yeah, okay, but it's below the error.
Okay, so one can go through and look at the pattern of deviations. So you know that if you make a lot of measurements, 1 out of every 3 or 4 is going to be more than 1 sigma away from the value that you describe. So one can look at the totality of electroweak measurements and ask whether there are outliers. So indeed, some experiments are more than, well, of course, you have to combine the 2 error bars on those numbers. But you can go through and ask how many measurements are more than 1 sigma away, how many are more than 3 sigma away. There are some examples of 3 sigma deviations. But in general, I think the pattern of deviations between the best fit standard model value and the array of experiments is really maybe even better than expected.
So I thought that the sigma was at the 5th digit, while it is much higher, maybe.
Oh, I'm sorry. The error is given for the width of the Z.
Yeah. Okay, now I
See,
understood
there's
the
an error of 1 and 2 in the 4th decimal place.
Okay, so it's less than 1
and the
sigma.
deviation is less than that. It's less than 1 sigma. Please. Oh, wait for the microphone.
Explain in detail the effect of the top mass in the ZBB bar partial width. The fact that there is a 2 0.96 instead of a 3?
Oh, it's only relevant because, as opposed to other electroweak corrections that I didn't discuss at all, because reactions that involve the top quark, let me draw one sample diagram again. Very often, these have an enhancement not only of the thing you would expect, alpha, there's some extra factor here of alpha weak over 4 pi. So this is already tenths of percent. But very often when the top quark is involved, there's an enhancement by mt over mw or mz squared. And so this can make it more important than other one-loop contributions, which is why I paid attention to it. The origin of these terms I'm going to discuss in lecture 5. So hang on until then. But it just turns out that this effect is numerically important, so I thought I'd throw it in.
For example, why it is not, I mean, if instead of a B, we have a down quark, we will have
I'm sorry.
a suppression M up over MZ,
yeah.
right?
So if there's a down quark here, VTD appears here. And actually twice,
okay.
right? Or VTS.
Okay, it's still top.
There's VTD is a very small number. There's a GIM cancellation. It's totally negligible.
Or we can also have an up quark,
Yeah, okay.
but it's a small mass.
But as I say, it's only when you have the top quark in the intermediate state that you get this enhancement. And only with the bottom quark is the CKM matrix element large enough that it's actually an important effect. Other questions? Okay, well, if you don't have them now, you'll have them later. You know where to find me. Otherwise, I'll see you tomorrow. Thank you.
Okay.